Welcome to Intro to Limits. In this video, we're going to talk about the idea behind the limit, what it is, and how we can see them both graphically and by using our calculators. So take a minute and work on the do now for yourself. So as I go to draw these figures, I'm going to cheat a bit because my program allows me to do it. I have a 6-sided polygon, a 10-sided polygon, and well, my computer only lets me go up to 16, so I guess we're not doing 20. 6, 10, and 16. What do you guys notice that's actually happening as the number of sides are increasing? What's happening to the shape of the polygon? And you might notice that first I started with the hexagon and then the decagon, and as you went up to the one with 16 sides, it's starting to get really close to a certain shape. And the shape that it's starting to get close to is a circle, right? As you have more and more sides, eventually it's going to be super close to a circle. I mean, look at the first one. If I bring this over, definitely not a circle. If I bring this one over, it gets kind of close. And then this one with the 16 sides, it starts to get really close to a circle. And I'm sure if you added even more sides to this polygon, that would look almost identical to a circle. And that's basically the idea of a limit. As you progress through a pattern, a sequence, or a function, as you keep going on, what's happening to your pattern or your function? In this case, as we progress through this pattern of increasing the number of sides, our polygon is going to look like a circle. Will it ever be a circle? No, because a circle has no sides. However, this pattern is going to get so close to being a circle in general, we're going to say that's the limit. That's its final endpoint. So with your calculator, take the time to evaluate these 5 values. So for my first one, I'm going to have 1 over 1 plus 1. You're going to end up with 1/2, or your calculator will tell you 0.5. For the purpose of this, please leave everything in decimals. It's going to be a lot easier to compare. For the next one, you're going to have 5 over 5 plus 1. And you're going to get 5 over 6, which is 0.83 repeating. The next one, 49 over 49 plus 1, so basically 49 over 50, is going to be 0.98. This one, 99 over 99 plus 1, will give you 0.99. And then the next one is going to give you 0.99999. It's basically going to be 9999. Oh my god, this is a lot of nines. It's going to be 99,999 over 100,000. So what do we notice about the value of the fraction as the x gets bigger and bigger? Well, as we plugged in larger numbers, you can see that all of your answers, the decimals, are getting closer to 1. So if you ever want to find out what's happening as you progress in this function as far as the limit goes, just plug in really large numbers and see what value you start to approach, right? I know that this isn't going to go up to like 50 because you can see that it kind of flatlines very close to 1 but never actually touches it. Now, if you want to think about why that actually happens, it's over here. We know that x over x is equal to 1, right? However, in this case, we have x over x plus 1. So at the beginning, adding a 1 threw off the function a lot, right? We went down to half. When your number started to get a little larger, the 1, a small number, didn't make as much of an impact. But when you're talking about hundreds of thousands, right? When you have 99,999, adding a 1 in the denominator isn't going to offset the actual fraction that much. Think of it like if you were to have $1 million, what's $1 extra to you? You know, it doesn't really change the entire function so much. So sometimes for limits, we can ignore the smaller numbers and we can get our answer that way. For example, here I could have looked at, well, x over x is 1. I know that my limit is going to be 1 in general. But we're going to have another video explaining all these methods later on. We're going to try this one again. Take your calculator, plug in values. You can pick whichever large numbers that you want. Start small, then get large, and see what's happening. For me personally, I went with 10, 50, 100, 500, and 1,100. The y values that I got were 0.1, 0.02. Oh, wait, nope, it was hold on. So I was right the first time. 1 divided by 50 is 0.02. 1 divided by 100 is 0.01. Divided by 500 is 0.002. Divided by 1,100, if you were to round it, you get 0.001, a little bit less than that. So based on picking these large numbers, can you figure out what's happening to the function? What number is it getting closer to? And that number is going to be 0. So we're going to say we're approaching 0, but never actually hitting it. If you're still having trouble thinking about it, take this one for example. 1 divided by 1 is 1. 1 divided by 2 is 0.5. 1 divided by 3 is going to be 0.3 repeating. As you progress and you divide by a very, 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 very large number, you're going to get smaller and smaller and smaller. But I mean, dividing by a positive number isn't going to give you a negative. So we get smaller and smaller, but we never hit the negatives. So we basically go down to 0. Now, there is a way to write this out. What we're going to say is we're talking about function f of x. And we're talking about the limit as numbers get infinitely bigger. So I'm going to say as x goes to infinity, as you get very large. Now, the notation for that is going to be lim for limit in front of the function. And right underneath it, you're going to have as x goes to infinity. So make sure that the way you write it, because I know my handwriting is not the best. If you were to have this on a line, maybe I can move this down. There we go. It's a big f of x and a smaller lim limit with the as x goes to infinity underneath. So again, this part is supposed to be the same size as f of x. Small first part, normal size actual function. Anyway, we just said that the limit as x goes to infinity of f of x is equal to 0. Anyway, actually defining what a limit is. So a limit is the value a function approaches at a certain x value. Now in this case, I made my x value infinity because I wanted to look at the limit as we get larger and larger. You do not have to do that. You can say the limit as x approaches to 3, and we're going to get to that in another video. Now, it can also be considered as a height that a function intends to reach. And the word intend is very important because, as we talked about in the do now, that polygon never became a circle. However, as you went on, it looked very close to a circle. For this function right here, this will never equal 0. There is no number that you can have where 1 divided by it is going to be 0. It just won't happen. However, we say that it gets very close to 0. So it's important to realize that the concept of limits doesn't mean that this function is going to actually equal 0. It just gets close to it. Now, if you were to actually put this graph in the calculator, hopefully you'd remember what this function looks like. Not like that. Now, with this graph, we're talking about the limit as x goes to infinity of f of x. So, as you look on this side of the graph, what's happening, right? Now, we've learned already that there is a horizontal asymptote going on in this graph, also a vertical one going down the middle. But my point is, because there's an asymptote there, we know that we don't actually touch 0, but the function gets very close to 0. Now, we might actually be used to expressing this as your long-run behavior. Sorry, not long-run behavior, end behavior. So with your end behavior, we're used to writing it as x goes to infinity, f of x goes to 0. And we're used to saying as x goes to negative infinity, on the left, f of x on the left of the graph is still going to 0. So basically, we can use what we already know to rewrite it as a limit, which has a lot of math being done with it, especially when you get to learning about derivatives. So I can also write on the left-hand side, we have the limit, although this time I'm going to look at the left side of the graph. So as x goes to negative infinity of f of x is still 0. So basically, you can switch either between limit notation or between the notation on the right-hand side to express end behavior. The choice is really yours. Now, let's talk about a cup of coffee. So let's talk about a cup of coffee. It's probably the most popular limit example. When you get a cup of coffee, it is piping hot, right? So or at least usually you don't drink it right away because it's too hot for you and it'll burn your tongue. Instead, you wait several minutes because the longer you wait, the more the coffee is going to cool down. Think about it this way. If you wait 2 hours on your cup of coffee, right? The longer you wait, the more it cools down. What temperature do you think it's going to be after those 2 hours? Is it going to be freezing cold? Because, if it just keeps cooling down, eventually it's going to hit a freezing temperature, right? But, if you ever have coffee, it never gets to freezing cold. That's why you order iced coffee if you want cold coffee. What it does get to is room temperature. So a cup of coffee, the temperature of it has a limit of reaching your room temperature. It's not going to cool down any further than that. If it is 90 degrees in your house, that's very hot. If it's 90 degrees outside, then your cup of coffee is going to stay at 90 degrees. If it is 65 degrees in your house, then that cup of coffee is going to cool down to 65 degrees. So when you actually do this the math way, keep that in mind. If you plug in 1 into this equation, you're going to get 100 degrees. If you plug in 3, you're going to get 71.875 after waiting 3 hours. If you wait 5 hours, it's going to get to 70.1170. If you wait 10 hours, it's going to get to 70.0001 degrees. So if you had to take a guess, what's the limit of this cup of coffee, the temperature for it, you're going to say that it's 70, because that's the room temperature. Now, you can probably see this one right away, because I see 70 as my constant here. Now, I know this function is going to get smaller and smaller, and you can figure that out if you just play around with it. For example, 1/4 to the first is 1/4. 1/4 to the second is going to give you 1/16. And then if you do 1/4 to the third power, you're going to get 1/64. And we saw in the last example, as your denominator increases a lot with your numerator staying the same, that the limit of this is eventually going to head to 0. It's getting smaller and smaller, which is making this whole piece of the function head to 0. So basically you have 70 plus something, 70 plus something smaller, 70 plus something even smaller, until eventually you kind of get 70 plus almost 0, which is just 70. So that's what's actually happening here. Now, do you need to do all this work in blue? Absolutely not. You put the equation in your calculator, you go to the table of your graph, and all you have to do is keep scrolling down to where your x values are getting larger and see if a pattern is emerging. Like here, clearly my numbers are going down to 70. So on your own, work with several functions and finding the limit of them. When you do that, be careful that you're reading if you're going to positive infinity or negative infinity, because if you're heading to negative infinity, make sure you go up on your table and you're looking for more negative values like -10, -100, -1,000, right? So read carefully and try to see either with plugging in values or by looking at the graph, can you figure out what value the functions are approaching? And that's all for this video.